Greetings, everyone. This is Professor Roman. Let us continue the group theory lectures. We have been talking about the Sylow theorems, and I want to look now at some uses, applications of these theorems. Let me go over the Cello theorem. I've collected it all into one theorem, as you know. Let me go over this very briefly. If G is a finite group, and if p to the n is the largest power of the prime p that divides G, then we have the following. The Cello p subgroups of G are precisely the subgroups of G of order p to the n. Second, the family of Cello p subgroups constitutes a single conjugacy class. And so if we take any Cello p subgroup S, the set of all Cello p subgroups that are conjugate to S, that's the conjugacy class containing S, is in fact the set of all Cello p subgroups. Another way to say that, more mundanely, is to say that every conjugate of a Cello p subgroup is a Cello p subgroup, and every two Cello p subgroups are conjugate. The number of Cello p subgroups, we denote by n sub p, is congruent to 1 mod p and is equal to the index of the normalizer of any chosen Cello p subgroup in G. So S could be any Cello p subgroup. Now, oftentimes, as we will see shortly, all we need to keep in mind here is that NP divides the order of the group. Fourth, a Cello p subgroup is normal if and only if it is unique, if there's only one Cello p subgroup. And fifth, a Cello p subgroup S is self-normalizing, meaning it's equal to its own normalizer if and only if NP is equal to the index of S in G. To be self-normalizing, as I mentioned last time, is to be as unnormal as possible. The only elements of the entire group that normalize S are the elements of S itself. The Cello theorems, along with group actions and some simple counting arguments we're going to discuss, provide powerful tools for the analysis of finite groups. And one area in which these tools exceed is in searching for normal subgroups, or showing that normal subgroups are lacking. So for this discussion, I'm going to assume, as always, that P denotes a prime, and I'm going to let Y sub P denote an arbitrary Cello p subgroup. I would rather have used S sub P, but that could easily be confused with the symmetric group on P symbols, so I've chosen Y sub P. If we survey the results that we have proven so far, including the Cello theorems, a corollary from Chapter 12, Corollary 12.9, we can collect the following tools for finding normal subgroups. And after I discuss these tools, we'll look at some examples. First, the kernel of any group action is a normal subgroup of G. Could be trivial, could even be the entire group. Those are not very interesting normal subgroups, but it might not be, in which case the kernel of the action could be a non-trivial proper normal subgroup, which is what we're really looking for. 2, a Cello p subgroup y sub p is normal, as we know, if and only if np equals 1. It's unique, in other words. Now, oftentimes, as we'll see, we can show that np it does equal 1 using these two conditions. And we can tweak these conditions a little bit to make the arithmetic a bit easier. First of all, if p to the n is the largest power of p that divides the order of g, and p to the n is relatively prime to np, because that's congruent to 1 mod p. So I can replace this divisibility condition by this. np divides the order of g divided by p to the n. This isn't a big deal, but it does reduce the size of numbers and makes the arithmetic simpler. Also, this condition can be written np equals 1 plus kp, where k is a non-negative integer. So both these conditions can be combined and will imply that the only candidates for the value of np, written as 1 plus kp, are the values that divide this expression, order of g divided by np. And as we're going to see, oftentimes it's possible to show that this condition is met only by taking k equals 0, in which case np is equal to 1. So just for the sake of our discussion, I'm going to refer to this condition that 1 plus kp does not divide order of g over p to the n for k positive, strictly positive, as the p condition. That's not standard terminology, but it'll be useful for our discussion. So if the p condition holds, there's a unique Sylow p subgroup, and so it's normal. And if the group is not a p group, it's a proper normal subgroup, non-trivial as well. It's just what we're looking for. We got two other tools here. If the index of h and g is equal to the smallest prime dividing the order of the group, h is a proper, non-trivial, proper normal subgroup of G. We proved this earlier. If H is a proper subgroup of G, but the order of H does not divide the index of H factorial, then the normal interior of H is a non-trivial proper normal subgroup of G. All right, let's see how these tools would be used. The P condition, by the way, is not very useful for P groups, because then the largest power of P that divides the order of the group is the order of the group, and there is a unique Sylow P subgroup, namely the whole group. And that's not, even though that's normal, it's not proper. So we get nothing out of that. Here's a group of order 9982. Prime factorization of the order looks like this. And it is just routine arithmetic to show that G has the 7 condition, that 1 plus 7k does not divide the product 2 times 23 times 31. In other words, the order of G divided by 7, which I think is this number. And all you have to do is take out Excel, or however you want to do it, to show that no value of k greater than 0 will divide, 1 plus 7k will not divide 1426. So Y7 is unique. there's only one Sylow 7 group, and therefore it's normal. This is remarkable power. We're able to show with just a little bit of arithmetic that any group of 9,982 has a unique subgroup of order 7, and the subgroup is normal. Okay. And this, you can see, would work for other orders. I just made this one up. I wanted product of primes here. So here's a more general kind of result that you can get from these techniques. Suppose the order of G is p to the n m. I want p to divide the order of G, so n is bigger than or equal to 1, and I don't want this to be a p group, so m is bigger than or equal to 2. And p doesn't divide m. I've taken out the largest power of p from the order of G. The p condition will hold whenever m is less than p, whenever this factor is less than this prime, because then 1 plus kp is, if k is positive, 1 plus kp is bigger than or equal to 1 plus p, which is bigger than m. Okay. And so the k condition holds. The p condition holds. So all groups of order p to the n, 2p to the n, all the way up to p minus 1 p to the n have a unique Sylow p subgroup, which is then a proper normal subgroup. So we got a whole bunch of orders here that this applies to. I did a little computer programming, and it showed me that among the orders up to 10,000, excluding the prime powers, there are only 569 of these orders, less than 6%, that do not satisfy the p condition for any prime p. So for the vast majority of orders up to 10,000, the p condition will work. You have to find the right prime p, and those groups will have normal Sylow p subgroups. So even this relatively simple criterion shows that there are very few simple groups, at least among this range of orders. And it attests to the usefulness of the p condition. It works, roughly 94% of the time, at least for groups of small order. But it doesn't always work, so we need to find other tools as well. And here's an example. If p is a prime, and it divides the order of G, but p squared does not divide the order of G, so p is the largest factor, largest power of p that is a factor of the order of G, then each of the NP Sylow p subgroups has order p. So these Sylow p subgroups are essentially disjoint. Their intersection, pairwise intersection, is trivial. Therefore, G contains exactly NP times p minus 1 distinct elements of order p, because each of this NP Sylow p subgroups has size p. Take away the identity, p minus 1 elements, all of which have order p. And because of the pairwise essential disjointness, there's no overcounts here, NP times p minus 1. And sometimes this simple counting argument applied to two different primes is enough to show that one of the corresponding Sylow subgroups has to be normal, that NP has to be 1. Here's an example. Let G be a group of order 30. 2 times 3 times 5. Then the NP condition only allows us to conclude that N3 is either 1 or 10, that the number of 3 Sylow subgroups is either 1 or 10. If you apply this for p equals 3, you get 1 plus 3k divides 10. That happens if k is 0, but it also happens if k is 3, because 1 plus 3 times 3 is 10, and that divides 30. Similarly, N5 is one of either 1 or 6. So the P condition is not working here. It does not give us a definitive answer concerning normality of one of the Sylow P subgroups. But if N3 is 10 and if N5 is 6, count the elements. There are N3 times 3 minus 1, which is 20 elements of order 3, and N5 times 5 minus 1, which is what? 4 times 6 is 24 elements of order 5. 20 elements of order 3, 24 elements of order 5 totals 44 elements, which is a bit difficult to squeeze into a group of size 30. So one of these, Y3 or Y5, must be normal. Unfortunately, it doesn't tell us which one, but that is still significant progress. Here's a more specialized application of this counting technique. You may know, and it can be shown, that integers of this form 2 to the n minus 1, I'll denote them by m sub n, are prime if and only if n is prime. These primes, so say 2 to the p minus 1, are called Mersenne primes. And these are the first few of them. So suppose that we have a group G whose order looks like this: 2 to the p times 2 to the p minus 1. And I'll denote 2 to the p minus 1 by q. Again, p is prime. So 2 to the p minus 1 is a Mersenne prime. So it's a Mersenne prime times the next number up. Then for NQ has to divide 2 to the p. And NQ has to have this form. This is Q. So it's 1 plus KQ, or 1 plus K times 2 to the p minus 1. But if k is bigger than or equal to 2, then this condition implies that NQ is bigger than 2 to the p, which violates this condition. So k is either 0 or 1. In the former case, YQ is normal. In the latter case, where k equals 1, NQ is 2 to the p. Set k equal 1 here. And since each Sylow Q subgroup has prime size Q, the 2 to the p Sylow Q subgroups account for this many subgroups times this many elements of order Q equal to the order of G minus 2 to the p non-identity elements. So there are 2 to the p other elements, but there's at least one Sylow 2 subgroup, and it has size 2 to the p. They all do. So it's unique. And Y2 is normal in G. So we can say then that either YQ is normal in G or y2 is normal in G. At least one of y2 or yq must be normal in G. And that's interesting enough to put in a theorem, which I have done here for future reference. Example, suppose the order of G is 12. That has this form. It's 4 times 3, so it looks like this Mersenne prime times 1 bigger than that. Then either y2 or y3 is normal in G. But we can do better than that, although it's going to require using most of the techniques we've been discussing. Suppose for a minute that y3 is not normal in G. Then y2 is normal, and it has order 4. Since we're assuming y3 is greater than 1, but y3 has to have this form, 1 plus 3k, and has to divide 4, the only choice is that y3 is equal to 4, so there are exactly 4 Sylow 3 subgroups in G. Again, if y3 is not normal, y2 is normal, and we can conclude from the arithmetic, the P condition, that there are that NP equals 4, that N3 equals 4. There are 4 Sylow 3 subgroups. Also, N3 is 4, but so is the index of any of these Sylow 3 subgroups. And so N3 is equal to the index of Ci in G, for I equals 1 to 4. So each of these Sylow 3 subgroups is self-normalizing. Now, let's let G act on the 4 Sylow 3 subgroups by conjugation. The kernel of the representation map is the intersection of the stabilizers of the elements of this set, the Sylow 3 subgroups. That is the intersection of the normalizers, because we're doing conjugation, we're acting by conjugation. But the normalizers of each of these is just the Sylow subgroup itself, because they're self-normalizing, and that intersection is trivial. So the action is faithful. Its kernel is trivial, which means G, the group G, is isomorphic to a subgroup of the symmetric group S4, because this has size 4. But the order of G is 12, which is half the order of the symmetric group S4. So G is a gigantic subgroup of S4, and we know that those are unique. Theorem 11.7. In fact, the alternating group is the only gigantic subgroup of S4. So G is isomorphic to A4. I'm sorry, did I say the symmetric group? The alternating group. Okay. So G is isomorphic to the alternating group. So what we have proven is that if G is not isomorphic to A4, then Y3 is normal in G. Because when we assumed Y3 was not normal, we concluded that G has to be isomorphic to A4. So the converse, contrapositive, G is not isomorphic to A4, then Y3 is normal in G. This is a key step in classifying all the groups of order 12, because we're going to have to eliminate A4 and eliminate D12 and say what else, and eliminate the abelian group, say what else is left. Okay. Well, if G is left, Y3 will be normal in G, and that'll give us a starting point for dissecting that other possibility for the group G. And we will do that later on. So I think this is a good example to study. It does involve the Cello theorems in the form of the P condition, and it involves using a group action, self-normalizing. So there's a lot of stuff going on here. The kernel of the representation, kind of bringing all our ammunition to bear on this example. And it's a good example to study to get the feel for how the study of finite group structure works. Okay. Let's not forget that this little tidbit, that if the index of a subgroup H in G is equal to the smallest prime divisor of the order of G, then H is normal in G. So here's a theorem and a simple example. If the order of G has the form P Q to the K, where P and Q are primes, P is smaller than Q, then the index of YQ, any particular YQ, any Sylow Q subgroup, in G is P. And that is then the smallest prime dividing the order of G, because I'm explicitly requiring P less than Q. So YQ is normal. So example, order of G is 75, which is 3 times 5 squared. Because 3 is less than 5, Y5 is a non-trivial proper normal subgroup of G. Well, we have gathered some rather powerful machinery for analyzing finite groups. So I want to put this machinery to use by completely classifying all groups G of order PQ, where P and Q are primes, and we'll assume that P is less than Q. So this does not cover the case of groups of order P squared, which we did discuss earlier in the course. First thing to note is that all Sylow subgroups of G are cyclic because they have order either P or Q, which is prime. And also, because the index of a Sylow Q subgroup, YQ, in G is P, and that's the smallest prime dividing the order of G, we know that there is a unique Sylow Q subgroup, and it is normal in G. Therefore, a simple counting argument shows that G is the join of these two subgroups, and this could be any Sylow P subgroup, and this is the unique Sylow Q subgroup. This is the essentially disjoint set product as well. And the product, we had a formula for the size of the product, and that will tell you that this is actually equal to G. Now, G is cyclic if and only if YP is also normal in G, or equivalently if and only if NP is 1. And we'd like to get some more information out of that. So notice that if NP is not 1, then since NP divides Q, that's one of the parts of the Cello theorem, we know that NP has to be Q, because Q is prime. Therefore, NP has the form 1 plus Kp, and that's equal to Q, and that's for some K bigger than 0, because we're assuming NP is not 1. and that implies that P divides Q minus 1. So what we learn from that is that if P does not divide Q minus 1, then NP has to be equal to 1. That's the contrapositive. And therefore G is the, in fact, direct product of these two cyclic subgroups. And therefore, because these are relatively prime, is cyclic itself. So this is progress. And here it is in summary. If the order of G is PQ with P less than Q primes, and if P does not divide Q minus 1, then G is the direct product of these two unique cyclic Sylow subgroups. And so is cyclic itself. Here's a quick example. The order of, oops, sorry about that. The order of G is 85, which is 5 times 17. 5 does not divide, that's P, does not divide 17 minus 1, which is 16. And so, G is cyclic. Okay, that's what we got from here. So that's pretty amazing stuff. Just a little arithmetic at this point, and we could determine that any group of order 85 is cyclic. Okay. For a more interesting, deeper example, let's go back to the case of order of G equals 30, which is 2 times 3 times 5. We saw in an earlier example in this chapter that by a simple counting argument, at least one of y3 or y5 has to be normal. We assumed that neither was normal, and we figured out how many Sylow subgroups there would have to be of each type. We counted the number of elements. I think this the total came out 44, somewhere around there anyway, and that's more than the size of the group. So we know one of the two must be normal. We can improve upon that. What we do know then, since one of these is normal, is that the set product, which I'll call H, is a subgroup of G. And it has order 15 because 3 and 5 are relatively prime. Moreover, since 3 does not divide 5 minus 1, we know that H is cyclic. Also, H has index 2 in the full group G, because H has order 15, the group has order 30. And so a theorem way back from chapter 8 tells us that H is normal in G. So H is a cyclic, gigantic, and therefore normal subgroup of G. Since H is abelian, being cyclic, these two subgroups of H are normal in H. So this is the situation. H is the direct product of these two normal subgroups, and H itself is normal in G, and H is cyclic. Now, there's a lot going on here. We ought to be able to get something out of it. Even though normality is decidedly not transitive, so we cannot conclude that because y3, for example, is normal in H and H is normal in G, that y3 is normal in G. That does not hold. H is cyclic, and that is very strong. Remember that in our study of cyclic groups, we learned that H has exactly one subgroup of every order D, say, dividing the order of H. So Y3 is the only subgroup of H of order 3. and similarly for y5. But if we conjugate y3 by any group element, A and G, then the conjugate y3 of A lies in the conjugate HA, but H is normal in G, so that's equal to H. So any conjugate of y3 is not only a subgroup of H of order 3, but it must be the only subgroup of H of order 3. In other words, it's equal to y3. A was any element from the whole group. We now know that y3 is normal in G. Essentially, the same argument applies to y5. And so we have learned that both y3 and y5 are normal in G. So that's pretty impressive, I think. The elementary counting technique told us one or the other of the two groups had to be normal, but that's a very simple counting technique. Can't expect it to give us complete information. We had to dig more deeply and use some of our machinery from the past to deduce the fact that both y3 and y5 are normal in G. So let's go back now to our general case. We have a group of order PQ with P less than Q. We've dispatched the situation when P does not divide Q minus 1, so let's assume P does divide Q minus 1. We know, in any case, that YP and YQ are cyclic. Let's say YP is generated by A, YQ is generated by B. We know that YQ is normal in G. Finding a normal subgroup of a group, of a finite group, is tremendously helpful in understanding the structure of the group. Since this subgroup is normal, if we conjugate the generator B by the other generator A, we must get a power of B, because it's still in the cyclic subgroup generated by B. And this integer lies somewhere between 1 and Q minus 1, because B has order Q. So, G, any group of order PQ for which this holds, must fit this standard template. It's generated by two elements. Its order is PQ. The order of the individual elements are P and Q. And we have this commutativity rule. It comes from the conjugation rule here. And of course, if this isn't valid, you don't have a group. So the groups G that fit this pattern have to satisfy this template, which has to be valid. And this is the T condition here. So we can account for all of the groups of order PQ where P divides Q minus 1 by examining these templates, figuring out which ones are valid. And then, of course, we do have to have this condition, P divides Q minus 1. But we already did this way back in chapter 6. This is the theorem we proved. Let P and Q be prime numbers for which P divides Q minus 1. And consider these standard templates, which are valid for T satisfying the T condition in this range. When T is 1, the template TQP1 defines the unique abelian group of order PQ. Or in other words, this cyclic subgroup we've already encountered in the case where P does not divide Q minus 1. For the other values of T not equal to 1, the templates are equivalent for all T, and so define a single non-abelian group of order PQ. So let's look at an example. Suppose the order of G is 21, which is 3 times 7. So now P does divide Q minus 1. 3 does divide 6. So G is either cyclic or it's non-abelian, and it fits the second statement here. If it is non-abelian, it is the essentially unique non-abelian group that fits this template. Here I have, 21. Okay, order of A is 7, order of B is 3, commutativity rule. The T condition in this case looks like this, easy to check, satisfied by T equals 2 and T equals 4. And I think those are the only ones that satisfy this. So G is the essentially unique up to isomorphism group satisfying either of these equivalent templates. And we now have a complete characterization of groups of order PQ. Here's the theorem. Let the order of G be PQ with P less than Q prime numbers. Let A have order P and let B have order Q. If P does not divide Q minus 1, then G is this direct product and it is cyclic. If P does divide Q minus 1, then G is one of the following. Again, cyclic. That's the abelian template. Or it is the unique non-abelian group defined by any of these templates because they're all equivalent. So I guess you would probably want to pick the smallest T. But you never know. You might encounter a group where BA equals A to the TB for some particular T. You want to know, does that fit this pattern? So that is a complete description of the groups of order PQ. We can do some more on this issue of groups of order PQ. We can actually find some of them and get a clearer description. When P divides Q minus 1, you might feel this isn't the greatest description of the non-abelian group. There's really nothing wrong with it. It gives you two generators, tells you their order, tells you how to multiply them together. So it's a complete description. But as we know, all groups lie inside some symmetric group, isomorphically. When P does divide Q minus 1, we can actually find the unique non-abelian group, let's call it G, that fits the valid template here, lurking in the symmetric group SQ. We can't always be so lucky as to actually, when the groups are complicated, actually find a copy in. We don't even know which symmetric group to look in. But let's go through this. Suppose T satisfies the T condition, so the template's valid. What we need is an element of order Q, an element of order P, and we need to have this relationship. Now it's going to be a little simpler in the argument we're about to give, if we think of SQ as the symmetric group on the set ZQ, 0 through Q minus 1, rather than what is traditional, and that is on the set 1 through Q. Okay. This is a combinatorial sort of thing. This is an algebraic sort of thing. It doesn't matter. Any set of size Q will do, because all symmetric groups on sets of size Q are isomorphic. But it will be easier to deal with this. Now, in SQ, we can easily identify an element of order Q, which is something we need in the template. That'll be our A. Just take the cycle, the Q cycle, 0 through Q minus 1. As to powers of A, which we're going to need, you can check, use induction or something. A to the K applied to I is I plus K mod Q. And I'm going to denote the residue class mod Q with this over bar. And this is why, really, I want to use this set rather than this set, because the residue classes would be, mod Q would be 0 through Q minus 1 rather than 1 through Q. So it'll work, but then you're going to have to deal with, well, if the residue is 0, replace it by Q, and it's not worth the trouble. So in words, applying A to the K to I just says add K and reduce. Now we need to find an element B in SQ of order P. And we need this relationship, this commutativity law, which again I write as a commutativity law. I'm sorry, as a conjugation law. If we assume that such a permutation B actually exists, then this is going to tell us how it behaves, because A to the T is BAB inverse, and to conjugate A, this cycle here, by B, we just apply B to each element in the cycle. So A to the T takes B of I to B of I plus 1, but you have to reduce I plus 1 in case it's equal to Q. Yeah, wrap it around to 0. On the other hand, we already know how to apply A to the Q, or A to the T, we just talked about it. You add T and reduce. So that means this side, which is equal to this, is also equal to this. And this is a recursive type formula that determines all the values of B, given the value B of 0. And it's this formula, B of I is equal to B of 0 plus IT mod Q. Well, we may as well choose B of 0 equal to 0 to simplify matters. B of I equals IT reduction mod Q. We have to check that this is a permutation, and that follows from the fact that T and Q are relatively prime. Q is a prime, T is less than Q, and bigger than 1. And so for any two elements in ZQ, B of I equals B of J implies IT bar equals JT bar, implies I minus JT congruent to 0 mod Q, which means that because T and Q are relatively prime, it means that I is equal to J, because I and J are between 0 and Q minus 1. So I has to equal J. So B is a permutation. And it satisfies this law. That's where we got it from. we also need to check that B has the correct order, P. Well, B of 1 is T bar, which is T, which is not 1, so B is not the identity map anyway. And again, an inductive argument shows that the jth power of B applied to I is IT to the j bar. So B to the P applied to I is IT to the P bar. And this, you may be wondering at this point, what about the T condition? We didn't use it yet. This isn't going to work without the T condition, and here is where we need it. T to the P is congruent to 1 mod Q. So this is just I bar, but I is in the range 0 to Q minus 1, so reduction does nothing. We get I. So B to the P is the identity map. So B has exponent P, but P is prime. So the order of B has to divide P. B is not the identity. The order is not 1. Therefore, the order is, in fact, P. And we can summarize. Let P and Q be primes with P less than Q. The standard templates, the valid ones, are equivalent, and so define an essentially unique group of order PQ. Moreover, one isomorphic version of this group is the subgroup generated by two elements A and B of the symmetric group on this set. So it's isomorphic to SQ. Defined by, here's A, it's this cycle, and B is given by B of I equals IT mod Q. Multiply by T and then reduce. So let's try an example. Suppose P is 3 and Q is 7. We've already looked at this. An earlier example tells us that the essentially unique non-abelian group of order 21 is defined by this template. And applying this theorem, A is the cycle 0 through 6, and B of I is 2I mod 7. 2 is the T here, this exponent. So what is B? Well, you can just figure it out. What does B do to 1? It sends it to 2 mod 7, so 1 goes to 2. Where does 2 go? 4 mod 7, which is 4. 4 goes to 8 mod 7, which is 1, so we've got this cycle. 5 goes to 10 mod 7, which is 3. 3 goes to 6 mod 7, which is 6, and finally 6 goes to 12 mod 7, which is 5. So these are the two generators for this group. And if you want to check that, if you don't believe this, the order of A is clearly 7. It's a 7 cycle. Order of B is 3. It's a product of two disjoint cycles of order 3, size 3, length 3, and order 3. And if we compute BA, we get this. If we compute A squared B, we get the same thing. So we have the commutativity rule.